Okay, good afternoon, everybody. It's 12:30, so let's go ahead and get started. We have been making a little bit faster progress than I anticipated. So today I could have started teaching you stuff, the next chapter, but I thought that'd be confusing because you'd be learning about something and then taking the midterm, and then I get a million questions. Is this on the midterm? No, then why are we learning it? So we'll just hold off until after the midterm to start on the new topics. And today I just thought I would do a bunch of problems. So I have a bunch of problems here, and we'll just work them. And honestly, I have no idea how long it'll take. Some of them are sort of crazy and hard, some of them hard to tell. So we'll just work through them. And then if you have questions or additional problems, whatever, feel free to ask. Okay? All right. So remember, we're dealing with energy and work, right? Okay, and so the way I always start solving these problems is using conservation of energy, right? Energy turns from one kind into another kind. And depending on how the problem is, you can write this as like gravitational energy plus kinetic energy initial equals gravitational energy, potential energy plus kinetic energy final, right? This is if you have a problem with only gravity and motion, right? This is the most general equation. This is slightly specific because this equation, for example, assumes there's no energy lost due to heat, right? There's no friction. There's no energy stored in a spring or anything else. So even though we often start problems with this equation as if it's a very general equation, remember it's not the most general. In some situations, you may have to add another term, like energy absorbed due to heat or friction or whatever, okay? I just always like to remember what the assumptions we're making are. Okay, now the really cool thing about, one of the reasons why this is so useful is that this potential energy due to gravity depends just on the height, not on the path, right? So if you have a y-axis here, and you have point A and point B, then the change in the potential energy, which is what we're really interested in, because we're interested in the difference between these two quantities, right? So delta U is just mgh, right? Where h is the height between them. All right, so you notice it depends only on their relative heights. It doesn't depend on anything else, right? It doesn't depend on whether they took a straight shot, whether they did a loop-de-loop, whether they went to Denny's and had the early bird special and then came back. It really doesn't matter at all, which is amazing. It's amazing that all the information about the potential energy is contained just in the initial and the final position. Does anybody know why that is?
Because it depends on displacement, not just its track.
Why?
Well, I think it has to do with work and the fact that gravity is only the distance traveled in the y component of direction is paid respect to because your force is gravity, and your gravity is purely has a y component, does not have a horizontal component.
So what if we had another nearby planetary object that was also giving us gravity? Then this wouldn't be true anymore? We had an x component due to gravity because...
Well, wouldn't you have to take the difference of find the acceleration of gravity then when it's the whole constant?
You'd still have to take the difference, but my question is, would it then depend on the path you took, or only on the initial and final position? My question is, why does gravitational potential energy only depend on the initial and final position and not on the path? That's the question. And I don't think it's because it's only in the y direction. I mean, another proof of that is you could rotate the axes, choose other axes, and it still holds true. Any other ideas? Because energy is conserved. Okay, but frictional force isn't true. This isn't the case for frictional force, right? Say you're pushing something. Right? Say you're you're playing with the slip and slide, and somebody replaces your slip and slide with sandpaper. Okay, so you're running along here, right? And you jump on the sandpaper, right? And you slide along it. A lot of energy is going to get turned into heat, right? And shredded buttocks or whatever. Okay. Now, if you slide on the slip and slide this way, and then you slide back, right? And then you come again. If you take 3 turns, it's going to be a lot more energy loss than just 1 turn, right? So there's a big difference between 1 trip and 3 trips, even though you have the same initial and final position. So in the case of friction, it does depend on the path. In the case of gravity, it only depends on the initial and final position. Right? So my question is, why is that true for gravity and not for other sources of energy, like friction? Yes?
Because you have to, because it's based on potential energy and not so much of kinetic energy as with like the friction, it's a lot of kinetic energy, and since it's friction, you're losing the heat. But when you're just focusing on gravity, it just has to do with gravity and potential energy you have.
Okay, but what about the potential energy makes this true?
Well, the potential energy is only based on how high off the ground they are.
Okay, but isn't that just another way of saying the same thing? I'm asking, why does the path only depend on the initial and final position? And you're saying it's because the potential energy only does, right?
Say that they go on a path where they go higher than point A. When they get back to point A, the potential energy that they gain has been lost.
Okay, excellent, good. Let's investigate that, because I think along that direction lies the solution, right? So say, instead of going straight here, right, and going from here to here, you lose potential energy, right? What happens if, let's make it simple, you take a detour up and come back, right? What happens is you go up, you gain potential energy. Now when you come back to point A, you lose potential energy. How much? Exactly the same amount as you had just gained, right? So imagine this is the simplest path. Now imagine any small deviation from that path. If you're going to come back to the path from that deviation, you're going to, right, imagine some deviation from this path, right, and then cut that deviation in half. The amount of potential energy difference in the first part of that is canceled by the second part. Any deviation from the path, your potential energy when you deviate from the path, you get a change in your potential energy. When you return to that path, that change is negated exactly by your return to the path, because the potential energy is linear. Okay, so so any deviation from the path, like if you go straight up and come back down, you gain additional potential energy, but then you lose it when you return to the path. Okay, so that's why it's true for gravity. Okay, now friction is different, right? Friction, you lose energy on the way up and you lose energy on the way down, right? So gravity has this linear dependence, which means you can gain and lose potential energy. Okay, so that simple fact about gravity makes a lot of physics problems a lot easier than they really have a right to be. For example, so let's do the first one. Sorry, are there other questions about that concept? Okay, if more come up, feel free to pose them later. So this one says, a light rigid rod is pivoted on a low friction horizontal axle. The rod of length L hangs straight down at rest with a small massive ball attached to its bottom end. Okay, so we have a rod of length L here with a mass M attached to it, and this thing can pivot like this. Okay, so it can go in this direction. You strike the ball, suddenly giving it a horizontal velocity so that it swings around in a full circle. Okay, so that it goes up to here. Right, and then comes back down. What is the minimum speed at the bottom required to make the ball go over the top of the circle? Okay, so the question is, what velocity do you have to give the ball here so that it makes it all the way to the top? Obviously, if you just barely touch it, it's going to go back and forth a little bit, not too high. If you hit it harder, it'll go higher. The question is, what's the minimum velocity necessary for it to make it all the way to the top? So how do we solve this one with energy? Okay, so if you could already see the solution, then you can drop a lot of the terms in advance, right? But if you're not sure exactly, if you don't quite have the insight yet to see how this problem gets solved, you can just start from this equation. You say, well, what terms are there in energy? There's no friction here, there's no spring, right? There's just motion and gravity. So I can say, all right, gravitational initial potential energy, kinetic energy initial, gravitational final energy, plus kinetic energy final, okay? Now let's simplify. Let's say, call this 0, and this 2L. All right, I can choose my axes to be anything. I could set 0 down to be negative a million miles, but it'd make my calculations harder. Why do I choose this one to be 0? Because then the initial potential energy drops out. Fewer terms is always better, right? Similarly, what is the final kinetic energy? 0. Why 0? I mean, I could hit this thing really hard and it could spin around for a long time, right? Why is the final kinetic energy 0? Well, the problem asks us, what is the minimum speed required to make the ball go over the top of the circle? That implies, what is the speed you need to give it at the bottom so it just makes it at the top, i.e., so it has 0 velocity at the top, right? That would be the minimum speed. Whatever speed you need here so that all of it gets turned into potential energy, and at the top, there's no velocity left. Okay, so final kinetic energy, 0. And so as our friend said, turn the kinetic energy into potential energy. Now the potential energy, very simple, right? It's mg2L. Kinetic energy, 1/2 mv squared. Now the mass drops out. Is that right? Yeah. Very easy problem, right? In the end, if you just use energy. If you try to use kinematics, you have to think about its motion in a circle, mv squared over r, tension from the rod, all this kind of stuff. You don't have to think about any of that. It doesn't matter that it's attached to the rod. It doesn't matter that it goes in a circle. All that matters is that you've given it kinetic energy here, and that's turned into potential energy. And potential energy is very easy to calculate. Kinetic energy is very easy to calculate with respect to velocity, right? So you can very easily relate velocity to height. That's the key here, right? That we can turn kinetic and potential energy back into each other, translating velocity into height. So another really nasty seeming problem solved very easily with energy arguments. Thank you, gravity, right, for having these properties. Of course, maybe you guys know gravity is a fascinating concept. It's the only fundamental force for which we have no quantum description. Right? Every other fundamental force, electricity, magnetism, the weak nuclear force, the strong nuclear force, we have an idea of how it works on a quantum scale, I mean a microscopic scale, exchanging of tiny little particles between each other. For gravity, we don't. We have no quantum theory of gravity. It's an enormous, outstanding theoretical physics problem. The person who solves that is going to be a giant on the scale of Einstein. So don't imagine that physics is all done, right? There's really big, obvious stuff left to do. Okay, and if gravity had a quantum nature, then there would be quantum gravity particles, which would be called gravitons. Do you guys know anything about the searches for gravitons? Do you know what a graviton is? Yeah, it's a communicator for the gravitational force. What does that mean? Right, well, it means it's like a little wave packet in gravity. It's a wave in space-time. It's like a ripple in space-time. There's an experiment in Louisiana and also in Washington, a really cool experiment looking for this. I'll just tell you about it in 2 minutes. It's, they have this setup where it's a leg 1 mile on a side, right? So this is it's a building. It's an L shape, 1 mile on a side, and they have a laser here that shoots against a mirror and comes back, and they measure how long it takes the laser to go there and back. And in doing so, they measure this distance very precisely. Okay, simultaneously, they measure this distance with another laser. So they have these two lasers. And they use interferometry to make it really, really sensitive. Anyway, they have these really precision distance measurements. Now, what they're hoping is that some graviton will be created by like a neutron star orbiting a black hole at really high speeds, or two black holes colliding into each other somewhere out there in the universe. Some crazy gravitational event will happen, creating a graviton which washes through the universe towards us. If a graviton comes, it's a wave in space-time, which means it's contracting space, contracting and expanding space. And what would happen is one of these legs would get shorter momentarily. And so what they're doing is they're looking for a wiggle like that, where only one leg gets shorter momentarily. So they have this really high precision instrument. And the reason they're at 90 degrees to each other is so they can see it no matter what direction it comes from. And they have one of these in Louisiana, one in Washington State, and there's one in Italy. So that if a real gravitational wave comes, you may be able to see it propagating across the face of the Earth, which would be cool. But it's a really difficult experiment because you have to keep this super quiet. Like their lasers are hanging from cables to try to be isolated. And if like a truck comes by, it shakes the whole thing. And so they have really complicated mechanical systems for isolating it from all sorts of acoustic noise. And then they've been running this thing for like 8 years, and they've just really seen absolutely nothing because you don't expect them very often. So it's a difficult experiment.
Would there be anything on Earth that would cause something like that?
I mean, it's just noise, just shaking. Isn't anything other than a graviton which could compress space. That's sort of the definition of a graviton. There's lots of things that could give you a false compressed measurement, but not lots of things that give you a real compressed measurement. Do all other fundamental forces come in indivisible packets? Yeah. So electromagnetism has the photon, right? A photon is the little wiggle in electromagnetic fields, right? The weak nuclear force has the W and Z bosons. The Z boson is a lot like the photon, but it has its mass. It's very heavy. Photon has no mass. And then the strong nuclear force, this is the one that holds the nucleus together. Or you ever wonder why the nucleus stays together? The nucleus is, a bunch of neutrons and protons. Protons are positively charged. Neutrons have no charge. Why don't these things just fly apart? The answer is the strong nuclear force. This thing has a particle called the gluon. Glues the nucleus together. I know, it's terrible. I am not in charge of naming these particles. If I was in charge, they would have very different names. Anyway, so all the other fundamental forces are understood on a quantum mechanical level. We have a quantum theory of them, and we've discovered each of these particles. We've produced and studied each of these. But nobody's ever made a graviton. It's just an idea so far. Okay, anyway, so gravity's fascinating. Yes?
What would you name the particles?
I named them after my kids, of course. No, there's a particle called the J psi particle. Okay, and this was discovered simultaneously by two different groups, one at MIT and one at Stanford. And they announced on the same day they discovered this particle. Actually, there's a longer story there because these guys were running a really long experiment. It takes a long time to accumulate data. These guys had a really powerful accelerator, but they had to know exactly where to look. So it's the kind of experiment where if you knew where to look, you could discover it in about 20 minutes. But not knowing where to look makes it pretty hard. These guys have been doing their experiment, and some people think that the information about what they were seeing leaked to the Stanford people, who then in one day were able to replicate their result and announce a result on the same day. Anyway, because there were two announcements, this guy from MIT, his name is Sam Ting, named it the J, which apparently looks like the Chinese character for his name. And the Stanford guys decided to call it the psi particle because that's sort of how it looks in their detector. And nobody could agree because people discovered it at the same time, so now we call it the J/psi particle, which is really stupid. Anyway, so whoever finds it gets to name it. Okay, back to mechanics. So next problem. A 2 kilogram block is attached to a spring, force constant 500. All right, so we have a block attached to a spring, okay, force constant is 500 newtons per meter. The mass is 2 kilograms. 2 kilograms. The block is pulled 5 centimeters to the right of equilibrium and released from rest. Find the speed of the block as it passes through equilibrium if there is no friction. Okay, so it's sitting at x equals 0, and then it's moved over five centimeters. Okay, and we're asked to find the speed of the block. So this problem is just like the other problems where you have gravity and motion, but in this case there's no gravity. Gravity, the potential energy is replaced by potential energy of the spring instead. All right, so you can start from E initial equals E final, right, where the initial state is having it be compressed, and the final state is it's back to equilibrium. Okay. Now, in the initial state, we have the potential energy of the spring, initial, plus initial kinetic energy, potential energy of the spring, final, plus final kinetic energy, right? So initially, there's no kinetic energy, right? You've pushed the block back, you're holding it there, it's stationary, but the spring is compressed, so there is some energy in the spring's compression, right? How much potential energy is in the spring's compression? 1/2 kx squared. Where did I get that? Well, I remember that that's the formula for potential energy of a spring. If I didn't remember, and I did remember that the force of a spring is negative kx, I could calculate this by doing the integral of f dx is negative 1/2 kx squared, right? The integral of x is just x squared over 2. So as long as you remember this equation for the spring, you could rederive this if you needed to. Okay, so that's 1/2 kx squared. That one's 0. What's the final potential energy of the spring? 0, because we're interested in the point when the spring is back at equilibrium, when x equals 0, right? So this one's 0, and this is 1/2 mv squared. And the question is asking us, what's the velocity? Well, they told us what the displacement was, they told us what k was, they told us what the mass was, so we can just solve for the velocity, right? Right, so it's pretty simple. And okay. See, so it's just the same as the gravity problem, except now instead of gravitational potential energy, we have potential energy of the spring. Okay, but then they make it a little trickier. They say, find the speed of the block as it passes through equilibrium if the coefficient of friction between the block and the surface is 0.35. So now we have friction in the game. So how do we solve the problem now? What else do we have to do? Add the work done by friction. To which side? Initial. Is there going to be work done in the initial state? No, the work is done by friction is here, right? I mean, I guess it depends on the sign you choose. But I write it like okay, so this is the term for friction. Where did I get this term? Well, the work done by friction is, we don't need to do the integral form, is F is the force times the distance, right? The force here is the frictional force, so it's the magnitude of the normal force times the coefficient of friction times distance. The normal force is just going to be balancing whatever the weight is of the block. So that's mg mu d. And here d is x. So that's the term for friction. Now, does it make sense to have it over here? Here's how I think about it. You have energy stored in the spring. That energy then gets turned into velocity and also into heat from friction, right? So the larger the coefficient of friction, the less energy you're going to have left over for this velocity. So that makes sense to me. As this goes to infinity, this goes to 0, right? Infinite friction would mean the thing just sticks there, even as the spring is compressed. Okay, so this doesn't add any complication really, except for mathematically. We know this number, we know this number, we know this number, we know this number. So it's just a slight complexity, right? So you solve this, it looks very similar, minus. All right, so you notice here the velocity depends on this term in a negative way. The smaller velocity comes from a larger coefficient of friction. Okay, so we have a different model here. It starts with the same problem, almost the same setup, but then they changed the universe we're working in so that there's friction. So we had to write a different initial and final energy equation to add another term because the universe had changed out from under us. Okay, questions about that one? Okay. So here we have some system that looks like this. It's a tabletop. There's a block on the tabletop connected by a rope which goes over a pulley, and there's a ball here. This one is 3 kilograms. This one is 5 kilograms. Okay. It says the coefficient of friction between the 3 kilogram block and the surface is 0.4. The system starts out from rest. What is the speed of the 5 kilogram ball when it has fallen 1.5 meters? Okay, so it's asking us about the velocity. So this is clearly an energy problem, right? You have potential energy here. You have frictional energy here. These two things are also connected, right? So they have the same acceleration. So we write initial energy is final energy. Okay, and so what terms do we have in the initial energy? Gravity, right? And we can write initial, but we know already that's 0 because everything starts at rest. So that's pretty simple. So the only thing we have in the initial state is gravitational potential energy. Then that gets turned into other gravitational potential energy. So we're interested in this difference, right? Plus kinetic energy, the final, plus the work done by friction, right? Just like the spring problem we just did. Potential energy of the spring was turned into motion of the object plus heat from friction. Here, the potential energy is going to be turned into the motion of the pair of objects plus heat from friction. Okay, so let's first think about this gravitational potential energy. Right, this is mgh. We can just do the relative height here. I mean, one thing we could do to be explicit is to say that the final height is 0 and that this one is 1.5, so that this goes away. Now, what mass do I put in here for the potential energy? Do I do 8 kilograms, 3 kilograms, 5 kilograms? Why 5?
That's the only one that's moving up or down.
It's the only one that's moving up or down, right? The potential energy here depends only on this mass. If this thing weighs 0.3 kilograms or 3,000 kilograms, it doesn't change the potential energy over here. It will change the acceleration of the system, right? Because it'll be harder to accelerate this thing if it's really heavy, but it won't change the potential energy of this guy. Okay? The mass of these two guys will come into the kinetic energy here. Okay, but this one is just the 5 guy, so this is 5 times g times 1.5 over here, right? And then the kinetic energy here we write as 1/2 5 plus 3, right? This is the mass. We're talking about the kinetic energy of the combined system. They both have kinetic energy. Even though one's hanging and one's sitting on the table, they have the same velocity because they're connected by a rope. So we treat them as one system with mass 5 plus 3. Do I need to think about it that way? Well, I could have written these as separate terms, right? A kinetic energy for this and a kinetic energy for that. And then, I mean, all I've done here is group with parentheses. There's no real physical insight there. The critical thing is noting that they have the same velocity. If you have V1 and V2, you're going to end up with one equation and two unknowns and not know how to solve it. Noticing that they have the same velocity is the key to simplifying that problem. Okay, so that's the kinetic energy term. And then we have the work done from friction, right? Work done from friction is, again, mg mu d, right? Now, what mass do we use for this one? The 3, right? This is the only one that feels friction. Okay? And then we have g, we have mu, which is given, and then we have the distance. How far does this thing go? Well, it travels horizontally the same distance that the other one slides. So this is also going to be 1.5. So now we know everything in this problem except for the velocity.
How do the two objects have the same velocity?
Why? How do you know they have the same velocity? Because they're connected by a rope. Okay? Questions about that one? All right. Let's see. Let's see if we can find a harder one. Okay. Okay, here, let's do a slightly trickier one. These sound like they're too easy for you guys. After a while, you do these problems, they all start to seem the same, right? And that's because there aren't that many terms in the energy formula, right? Kinetic energy, potential energy, work loss due to heat or friction, that's all that there is in these problems. Every single problem is just a different way to mix that information up and connect it to each other. Okay, so here we have an 8-centimeter rod, pivots around its center. Okay, so here's the axis, and half of it is 40 centimeters. A half a kilogram rat sits on one end. Okay, so here's our rat. Looks more like a cat. Half kilogram rat sits on one end, and so this is a half a kilogram. Anybody know, is that a reasonable amount for a rat? A 1 pound rat, is that pretty typical? A 10-pound rat? Yeah, cats weigh 10 pounds. If you saw a rat the size of a cat, you're probably in the New York City subway. Sorry? It's a possum, yeah, okay. All right. And on the other side is a 0.2 kilogram mouse. Okay, so apparently a mouse is smaller than a... Oh my God. All right. It looks more like an ant. Okay, anyway, a 0.2 kilogram mouse on the other side, okay? Now the question is, because this guy is heavier than this guy, this will eventually rotate like this, right? Where the rat is hanging on for dear life here, and the mouse is balancing here. Okay? The question is, what are the animal's speeds when they reach the vertical? Okay, so you started them off here. There's an imbalance in the masses. They flip this way. What are the animal's speeds? So how do we set this one up? All right, so what are the energy terms? Well, in the initial state, there's potential energy, right? Gravitational potential energy. We could write a kinetic energy term just to make sure we're thinking about it, but there's zero velocity in the initial state, so that's zero. Right? And then there's gravitational potential energy plus a final potential energy, right? Which is the rotation velocity. And is there anything else in this little rat mouse universe? No. right? So that's it. So now when we do potential energy, often we choose one position to be 0 to make it simple, right? Either the initial state to be 0, the final state to be 0. So here there's a couple different choices you could make, right? You could choose this to be 0 here, so that the initial state has no potential energy. You could choose, 0 to be down here, 0 to be down there. It doesn't really matter. Because what we're interested in is this change in potential energy, right? So let's just choose 0 to be here. And then we just need to calculate this change in potential energy and relate it to the kinetic energy, right? So the change in potential energy is just relative to the heights and the masses, right? So for the mouse, it's m mouse times g times, let's call this L, right? And then for because the mouse is on top, right? And the rat is going to be m rat times g times minus L, right? So it's GL mm minus mr, right? Plus 1/2 mv squared. Okay, now let's think about whether we got the signs right. This guy here, this has to be positive, right? Because velocity squared is positive, mass is positive. This thing has to be 0, so this one should be negative. The rat is heavier than the mouse, so this is in fact going to give us a negative number. So it looks like we chose our axes all consistently. And we can solve for the velocity we can solve for their velocity. Now what do we put in here? What m is this? Total, right? And so again, we don't have to worry about the whole rotational business. Right? Rotating things make everything much more complicated. But we don't have to worry about it. We just have to worry about the initial configuration and the final configuration. Thank you, gravity, right? Okay. Here's another one. Okay. A variable force F is maintained tangent to a frictionless semicircular surface. All right. This one's impossible to understand without a diagram. So we have a hemisphere like that of radius A. Now here we have a spring which is wrapped around this hemisphere. Okay? And there's a block here. A variable force F is maintained tangent to the surface. So whatever this F is, it's pulling it along this crazy bump. By slow variations in the force, the block is moved and the spring to which it is attached is stretched from position 1 to position 2. Calculate the work done in terms of the radius A and this angle theta. What? Right? What is this problem doing? So first of all, let's reread it because it has some interesting words in it. By slow variations in the force, a block is moved and the spring to which it is attached is stretched. Why did they say by slow variations in the force? That seems to me like either it's Obi-Wan Kenobi talking to us or it's like some special words that they're hoping to communicate some physics to us, right? It's like when they say a system in equilibrium or, at rest, and you're supposed to translate that to zero velocity or zero net force or something. Why do they say slow variations in the force? What's that?
Changing acceleration.
There is changing acceleration or there's no?
Not necessarily. So.
I thought that they were trying to make it so that they're always in constant velocity, so the forces are always equal.
Okay, any other ideas?
No,
I'm sorry?
no, velocity.
Yeah, so basically it's telling us there's no kinetic energy, right? It's very slowly being moved. Okay, it gets moved and then it gets moved. We're interested in the initial and the final positions, and there's no kinetic energy in either case.
Period again, please.
By slow variations in the force, a block is moved and the spring to which it is attached is stretched from position 1 to position 2. So that's just another way of saying final velocity is 0. Okay, so there's no kinetic energy in the initial state, no kinetic energy in the final state. What is there in this problem? There's the potential energy of the spring, and there's gravity, right? And the only reason this is different from any other gravity spring problem is that it gets wrapped around this block, right? Why does that matter to us? How is that going to affect us, how we solve the problem? Do we have to worry about like the normal force of this thing? No, that's all just going to get balanced, right? So why do we have to worry about it? Well, remember, it asks us to calculate the answer in terms of A and theta. So when we calculate the gravitational potential energy, we need to be able to calculate the height in terms of A and theta, right? And then we're interested in how far this spring is stretched, because the energy stored in the spring is 1/2 kx squared, where x is how much the spring has been stretched from equilibrium. So to calculate x, we're going to have to do that in terms of A and theta. So really, this problem is the same as just a problem where a spring is getting pulled in one dimension, but they've bent the axis for us to make it a little more complicated. Okay, so what we can do is just say the potential energy from gravity gets turned into the potential energy from the spring, right? You could start from the general equation of initial and final state energy, but there's only spring energy in the initial state and gravitational energy in the final state, so it doesn't matter. And so the gravitational energy is mg times delta y, right? Well, what is delta y in this case? So we just need to convert it to a sine theta. Right? So we just need to express the energy terms in these quantities that they've asked us for. Okay, what about the spring? Well, this is 1/2 kx squared. How do we write x squared here? A times theta, right? The distance around the curve. Okay, so the total energy that's the whole problem. So it's often the case with these physics problems, they seem complicated to set to when you read them, but if you set them up correctly, the math is pretty straightforward. If you get into really hairy math, that often is a sign you've done something wrong.
So why is the potential energy from gravity equal to the potential from the spring? Because aren't they both?
I'm sorry, no, you're right.
Not in the same direction.
Thank you. And you might think, well, that's sort of unfair. Like, why do they write these problems to be so convoluted when in the end the solutions are pretty straightforward, right? But remember, that's what physics is. When you're trying to solve a physics problem in real life sometimes gives you a complex sounding problem. It's a real achievement of physics when you can turn a complex real-life problem into a simple model that you can handle easily with the tools you have. That is the core of being a physicist. It's figuring out how to use the models you have to apply to real situations. So that's why a lot of this class seems to be extracting simple math situations out of complex seeming problems. Okay? Okay, so here's another nasty looking one found in the book. Okay, the gravitational pull of the Earth on an object is inversely proportional to the square of the distance of the object from the center of the Earth. Okay, so we already know that probably, but let's just write that down. It says The gravitational pull is proportional to the square of the distance of the object from the center of the Earth. Okay? At the Earth's surface, this force is equal to the object's normal weight mg, where g is 9.8 meters per second squared, and at large distances the force is 0. Okay, so that tells us that we can write this force as mg I get that right? Yeah, so this is distance from the center of the Earth. This is the radius of the Earth. So they've told us that it's proportional to 1 over r squared, fine. And then they tell us at the Earth's surface, the value is mg. So I try to set this up, put it in the right constants, so that if you plug in the Earth's surface for little r, you get mg as the total answer. Okay? So far we've translated what they told us into math. Okay. And at large distances, the force is 0. So that makes sense. As r goes to infinity, the force drops to 0. Now the question is, if a 2,000 kilogram asteroid, 2,000 kilograms, I'm sorry, 20,000 kilogram asteroid, thank you, too many zeros, falls to Earth from a very great distance away, what will be its speed as it strikes the Earth's surface? Okay, so it falls to Earth from a very great distance away. All right, so initial position, r is basically infinity. Final position, r equals re, right? A 2,000 kilogram asteroid falls to Earth from a very great distance away. What will be its speed as it strikes the Earth's surface? And how much kinetic energy will it impart to our planet? Ignore the effects of Earth's atmosphere. So basically they're asking, so it says, what will its speed be and how much kinetic energy will it impart? Well, those two are obviously connected, right? Its speed will be determined by its kinetic energy. So let's just calculate the kinetic energy. So how do we calculate the kinetic energy this thing gains from falling from infinity to the Earth's surface? So why is this thing gaining kinetic energy, first of all? Gravity is doing work on it, right? It's turning, or as you said, it's turning gravitational potential energy into kinetic energy, right? So it starts out with a huge amount of gravitational potential energy because it's basically infinitely far away. And it falls and turns that into kinetic energy. Now, we often write gravitational potential energy as mgh, right? Can we write that here? Can I use mgh and plug in h equals into infinity? No, why not? I mean, then I would get, like, I'd say, well, mgh equals 1/2 mv squared. Okay, v is in infinity. Is that true? I mean, the asteroids hit the Earth at infinite speed? No. Even if it wasn't due to relativity, that wouldn't be true. So why doesn't this work here? Because this assumes that h is small compared to your distance from the center of the Earth, right? If you're on the surface of the Earth, which is very large, and you're doing problems about shooting baseballs or whatever, it doesn't really matter. You can assume that g is constant and do your calculations and get the right answer. Because the change in g from here to here is really tiny. If, however, your scale is this, right? Here's the Earth, here's you, and we're talking about some asteroid on a kill trajectory, then obviously, do you guys see that they dug up that Russian asteroid last week? No. Remember that one that like exploded over Russia last year? Its final resting point was in a lake with this huge hole in the ice and buried itself in the bottom of the lake. And they had to wait for, obviously, summer and thaw, and they dug the thing up. It's pretty cool. Anyway, obviously the force of gravity is going to be very different here to here. The force of gravity here, we were told, is basically 0, right? So we can't use mgh. But how did we get mgh? We got mgh by saying, well, the work is integral of the force dotted with the distance, right? And we said, well, the force is just mg, it doesn't change. So then this just becomes h. But that's not true anymore, is it? Now the force changes with h. So we need to calculate what this obviously this is almost the right answer, right? We just need to know what is the gravitational potential energy, which we can convert into kinetic energy. So the question is, what is this work done by gravity, right? And so we need to do this calculation, where F is this guy. Okay? But this is a vector, so let's think about the directions here. If we set this to be positive r, what's the direction of the force? Negative, right? Okay, so is negative. Okay, now I've gone from a vector equation here to a one-dimensional equation here. And I've said these two vectors point in opposite directions. And so here I'm just writing scalars, and I put a negative sign to reflect the fact that the vectors are in opposite directions. Okay? There's lots of different ways to do this mathematically. You could choose your axes however you like. This is the way I did it. Okay, now we know what F is. It's mg re over r squared. Right? So this is equal to negative the integral of, I don't know about you guys, I like writing the infinitesimal first, so I remember what I'm integrating, and then put the thing I'm integrating. Mg re squared over r squared. And the integral goes from where to where? From infinity to radius of the Earth, right? Okay. And if you had done this differently, right? Yeah, anyway, it doesn't matter. But okay, so we have to do that integral. Now, mg re comes out of the front, right? Negative mg re squared times the integral dr over r squared. Right? So not that hard an integral. What's the integral of 1 over r squared? Negative 1 over r, right? So this becomes mg re times 1 over r, evaluated from re to infinity, right? And so r at infinity is obviously 0, so it doesn't matter. So this just becomes, oops, this is a squared here, right? And so this just becomes mg re. And because of the mass of this thing and the large value of the radius of the Earth, I got 1.25 times 10 to the 12 joules, right? Which then, if you translate into velocity, is a blistering 11,000 meters per second. Okay. Okay, but how realistic is this? I mean, asteroids that do hit the Earth, is their speed mostly affected by the gravity of the Earth? No, what is their speed mostly affected by? The gravity of the sun, right? We just happen to get in the way. This thing is either heading towards the sun or orbiting the sun, and we're just in its path. Yes, our gravity will affect it. It's more likely to pull it in towards us, but mostly it's going to be affected by the gravity of the sun, which means these things are probably going even faster than if we had just pulled them in with our own gravity, right? Okay, now most of the problems we're going to do happen on Earth, and you don't have to worry about doing the integral and calculating the work as an integral. But just remember the assumptions inherent in the solutions you've made. Yes?
How do you assume that at distance infinity away, how do you assume that potential energy due to gravity is zero?
Okay, so good question. Well, let's think about it. What do we know? At infinite distance, we know there's no force, right?
Yeah.
Okay. Now, can you say the potential energy is 0? Does that have meaning? No, because the actual value of potential energy is not relevant, right? You could add 1,000,000 to any potential energy as long as you're consistent, and it wouldn't change the answer. So what we're interested in is the difference in potential energy between two positions, right? So I never say here that potential energy is 0, I think. what we're doing is we're calculating the work involved in moving from one place with one force to another place and moving through the gravitational field. And so we're calculating the difference in the potential energy here. That's what the work is. Okay? So we said the force is equal to 0 at infinity, not the potential energy. And in the next chapter, after the midterm, we're going to analyze this in more detail. Potential energy functions, how to derive forces from potential energies, this kind of stuff. But we won't get into those details now. Okay, let's do a problem like this. Okay, so we have a pulley. Any other questions about that? Okay. We have a pulley and a rope and two masses. Okay. This one is 20 kilograms. This one is 10 kilograms. Okay. Both of these guys are sitting on a surface. Okay. So the masses of blocks A and B are 20 and 10 kilograms respectively. The blocks are initially at rest on the floor and connected by a massless string passing over a massless and frictionless pulley. Okay. As an upward force F is applied to the pulley, find the accelerations of block A and block B for three cases. F is equal to 124 newtons. F is equal to 294 newtons, or C, F is equal to 424 newtons. Okay? So how do we find the accelerations of these blocks? Well, let's think about an individual block, right? What are the forces on this thing? Right, there's gravity. There's a normal force. And then there's tension, right? Okay? Now, what happens if the tension is less than the gravitational force? Stays on the ground, right? And then the normal force is equal to mg minus the tension, right? Okay. What happens if the tension is greater than gravity? Well, then there is no more normal force, right? Because the thing is not pushing against the ground anymore, and the thing will accelerate. Right? So it's only in this case, when the tension is greater than the force of gravity, is this thing going to lift off the ground. Tricky thing is that these guys have different masses and therefore different weights and therefore different dependencies on this, right? Okay, now how does this tension relate to the force? The force is pulling on the pulley. We're interested in the tension. What's the relationship? Is the tension equal to the force? Is it equal to 7? Is it equal to 2? What is the relationship between the force and the tension? Well, let's think about a free body diagram for the pulley. All right, because that's going to relate the force and the tension. So what are the forces on the pulley? 2 tensions and 1 pulling force, right? If this thing was in equilibrium, then makes sense, right? So basically the rope and the pulley splits the force into two pieces. Okay, so we know the thing will accelerate only if the force is large enough. Okay? So in case A, okay, so what is the weight of each of these guys, right? This is 10 kilograms, so the weight is 98 newtons, right? This one, the weight is 196 newtons. Okay, so in case A, is that really 124? Right, okay, so in case A, what's the force on each block? What's the tension here? Well, it's the force over 2 62 newtons, right? So is anything going to happen? The force is not sufficient to pull either of them off the ground. So acceleration A equals acceleration B equals 0. Okay. Case B, the tension is still half the force, but in this case, it's 147 newtons, right? And that is enough to lift block B, but not enough to lift block A, right? So acceleration of A is equal to 0. How do we get the acceleration of B? Well, remember our old friend, right? So what is the net force on this thing? It's 147 minus 98, right? It's the tension up minus mg down, right? 49 newtons. The force is 49 newtons, so the acceleration is 49 newtons over 10 kilograms. Okay, so now you get the idea. Case C, the tension is still the force over 2. 424 is the force, so the tension is 212. So I can do my math right, yep. So the net force on A is 212 minus 196 is 16 newtons. So the acceleration of A is 16 newtons over 20 kilograms. The force on B is 212 minus 98 newtons, which is 114 newtons. So the acceleration of B is 114 newtons over 10 kilograms. All right. Okay, let's do one last one. Okay, here's the problem with a monkey and a banana. All right, so we have a pulley, and there's a chain, and over here there's a big bunch of bananas. Okay, and there, over here, there's a monkey holding on to the rope. It's got a long tail. All right, it looks like a squirrel. Squirrels like bananas too, right? Okay, so monkey is holding onto the rope. Bananas on the other side of the rope. Monkey is 20 kilograms. Monkey. Everybody know if that's reasonable for a monkey? It certainly would be killer for a squirrel. That'd be a scary squirrel. That's probably some horror movie on late night. 20-kilogram monkey is a firm hold on a light rope that passes over a frictionless pulley and is attached to a 20-kilogram bunch of bananas. So the monkey and the bananas are the same weight, same mass. The monkey looks up, sees the bananas, and starts to climb the rope to get to them. A, as the monkey climbs, does the distance between the monkey and the bananas decrease, increase, or remain constant? So what happens?
I think it would increase.
The distance would increase. Why is that?
Because as the monkey pulls down on the pulley or the rope, it will remain in the same spot, but the rope will move
Okay, so you're saying you pull on the rope, bananas go up. True. But what happens when you pull on the rope? Does he stay in the same position? He's not standing on the ground, right? He's hanging on the rope. So to pull on the rope, you're like climbing the rope. Actually, in fact, it says the monkey climbs, right? As the monkey climbs, do the bananas move up, move down, or remain at rest? I'm sorry, wait, first, I misread the question. Part A is, as the monkey climbs, do the bananas move up, down, or remain at rest? Okay, so as the monkey climbs, the bananas move up, right? Bananas go up. Okay, next part of the question. As the monkey climbs, does the distance between the monkey and banana increase, decrease, or remain constant? Okay, so what's your thought now?
Well, so I guess if the monkey were climbing, the bananas are being pulled upward with the same force as he is pulling himself upward with as well, so I guess they would both rise at the same rate.
All right, so let's think about the free body diagram, right? For the monkey and for the bananas. Force on the bananas is mg down. Monkey also has mg because they have the same mass, right? Force up on the bananas from the rope is tension. Monkey is holding the same rope, right? So the forces on both of these guys are the same. Right? So if the monkey goes up, the bananas go up. If the monkey goes down, the bananas go down. Right? So the distance stays the same. That's sort of cruel, right? Can we try it? Bring in your monkey, we'll try it. I'm sorry? Yes, excellent. So the distance stays constant as long as this model applies, right? Once the bananas hit the pulley, right, they're no longer freely moving. They just become, then it's just a monkey climbing a rope, right? The pulley becomes irrelevant once the bananas get jammed in the pulley. But assuming that the pulley is like infinitely high up, then the monkey could climb forever and never get to the bananas. It's so cruel, I know. No monkeys were hurt in the construction of this problem. Okay, next part of the question. The monkey releases her hold on the rope. Oh, it's, yeah, you know, there are female monkeys. The monkey releases her hold on the rope. What happens to the distance between the monkey and the bananas while she is falling? Stays the same. Why? Right, so what happens when the monkey releases the rope? What are the forces on the bananas then? Just gravity, right? There's nothing, nobody holding that rope, so it might as well not be there. So when the monkey lets go, gravity's pulling it down, gravity's pulling the bananas down. So it's falling, but the bananas stayed in the same place no matter what this monkey does, right? Next part of the problem, before reaching the ground, the monkey grabs the rope again to stop her fall. What do the bananas do? So do the monkey and the bananas slow down at the same pace or at different paces? Same, right? So the bananas don't change their position relative to the monkey at any point in this problem. Right? There's nothing the monkey can do to change her position relative to the bananas. Climbing the rope doesn't help. Falling on the rope doesn't help. Grabbing the rope doesn't help. Right? It's a particularly cruel setup.
In this picture here, why doesn't the monkey just grab the bananas? Because her arm is tied. Look at it. Look at it. You know it's just out.
You know, if this was a physics major undergrad, then yes. But they put a monkey in because it's not as clever as you. Okay? I'm sure if you had a monkey, you would train it to be that clever. Yeah. Teach the monkey physics and it would know it was futile, right? Why would it even be pulling on the rope if it had solved this problem? Okay. Where do you get an infinitely high pulley? Yeah, that's another good question. On the world of dumb monkeys, that's where you find this. Okay, any other questions? So remember, next week, midterm review. If you have trouble with the practice midterm, send me an email. I have my office hours tomorrow morning, so come by with the practice midterm if you're struggling with part of it. Okay? All right.